Okay, this is the problem 5-87. I went ahead and brought in the information from the 586 because you're going to need to know that to do this to do this problem. So here you have two shafts made of A36 steel, same material, each has a diameter of 25 millimeters. Alright, so the first thing I would recommend is doing is a free body diagram. Now, these are fixed here and fixed here. So if you draw the free body diagram of this shaft here, let's see if I can do something kind of rough. You would have a shaft like this. Let's see if I can get a circle here. We'll actually do ellipse here, see if this will work. We have a gear. Oh, that's not very good, is it? Hopefully I can draw ellipse, let's see. Kind of like this. I'll slide it in. Here, kind of like that. Okay. Well, what's taking place here is you have a torque that's been applied of 500 Newton meters this way here. Now this guy here, he's fixed here too, so he's going to try to push back against. Now if he wasn't fixed, he couldn't push back. So we're going to, oops, let's do it again. Draw the arrow going back this way here. Like that. Alright, so now we're going to have this one go the opposite direction. So we believe that it's going to go back this way. It's going to resist, and this would be the torque at A. And then we can put a value of this was 500 Newton meters. Now this force right now we have no idea what it is, so we'll put it as force like that. Alright, we'll do the same thing for the small one. Its free body diagram would look something kind of like this. Again, we'll try to draw the ellipse. It's a smaller gear. Going to go down by like this. Now it has no torque. I mean, there's no torque being applied to the shaft. So the only thing it's going to resist is this gear. Since this force here, you're going to have another force that's pushing back this way, like this. I'll do it with a vector. Pushing back like that. So it's going to try to spin this way. So to resist it, this reaction is going to go this way. And this will be the torque at B. Alright, now we can write our equations. So when we do this one here, we can say the torque at A plus the force, and we're going to multiply it by this distance here, which is the moment arm, which is 0.1, minus the 500 must equal 0. So there's one equation. Our second equation here would be the torque of, torque of B minus the F. Now it is going to be, it's a 50, so it'd be 0.05 is equal to 0. Alright, so there's our two free body diagrams, and there's our values. Okay, so now let's see here. We could substitute back in. We could solve for, let's see what we could do here. We could solve for force. It really doesn't matter which one. We'll just take this one, and we can move this to the other side. So then we could say that TB is get rid of that. Sorry, is equal to F times 0.05. And then we could say that F is equal to TB times 0.05. We can take that information right there and we can put it back into the other equation. We'll do that. So that gives me TA plus, and then 0.10. When I put it back in here, we're going to multiply the 0.10 over that, which would give me 2 TB minus the 500 is equal to 0. Alright, so we got that. Now the thing that's maybe confusing with this problem is, and if you think about it, let's talk about this. where these gears meet up here, and there's been a force applied. And I'm going to draw in these radiuses. I think this will make you understand it. If this has a radius of 50, so between here and here, 50 millimeters or 0.05. The radius between here and here is twice as much, so this is 0.10. Now we know that arc length along here is an arc length. Say arc length is always going to equal to the, we can call this the angular twist, which are angle twist times the radius. So we'll do that for this one right here. And could we not say that theta times 0.05 is equal to the arc length here, right down here? Okay. Now we'll set that arc length equal to this one. And we'll call this theta for the small gear, so I'll put an S here. Arc length for the larger, isn't that going to be theta larger gear times 0.10? Okay, so now we're going to set these two. We know this one's equal to this, so just come down here. We'll say theta of the small gear times 0.05 is equal to theta of the large gear times 0.10. If we divide this, can we not say that theta of the small gear is going to equal to 2, better do a better theta of the large gear? Or we could say the theta of the large gear is going to be 1/2 the angular twist of the small gear. So that's really critical information, and that's important to obtain. Alright, so now we can go back, and we know, based upon this, that the values to find angular twist is again going to be TL over J times G. Alright, so we're going to use that information, and we can say the torque at A, and let's see how long that is. That's a 1.5 millimeter shaft. I'm going to put the JG down here. Now, they have the same diameter and the same material, so there's no real reason to do the calculation here. And we could come back here, and we know that the angular twist of the small gear must be equal to the large gear. So we can go ahead and multiply this side, because this is, we're going to figure this for the small, times the torque at B times its length, and this length is 0.75 right here. This is a good problem. And again, we'll divide that by the JG. Alright, so now we can start canceling things out. We can cancel this out here. Obviously, we can cancel these out here. So if we do that ratio here, we can say that TA times 1.5 is equal to 0.375 TB. Now if I take TA and I divide it by 1.5, I'll get 0.375 divided by 1.5. Okay, so now if I multiply that by 4, I get that. So that's TA. Oops, sorry, thanks. Hang on, let me fix this. This over here, this TB. I better be careful. TB. TB. So that's going to equal to 1/4 TB. Okay, so that's important. Let's write that down. So TA is equal to 1/4 TB. So now I have this equation right up here. So let's put that back in. Can we not say that 1/4 TB plus 2 TB, move the 500 to the other side, is equal to 500. So again, I'm substituting back in this equation here. When we do that, we'll get 2.25 TB as equal to 500. I'll get my calculator here. I'll take 500 divided by 2.25. 500 divided by 2.25 gives me a value of 222.22. TB is equal to 222.22. And again, that's going to be newtons times meters. Now, all you have to do here is plug that back into here and solve for TA. When you do that, you'll find that torque A is going to give you a value of 55.56. So we got our two torques. It's a good problem. I really like this problem. And now it asks us for the angular twist using the torque at A. So can we not go back, and we know that theta is going to equal to the torque times the length over the polar moment inertia times g. We will use this value here of 55.56. We know the shaft is 1.5 long. We know J is going to be pi divided by 2 times the radius, and that's going to be 0.0125. We'll raise that to the 4th power. We look up the G value for the material, and that'd be 75 times 10 to the 9th. We run that value, and we will get theta as 0.02897 radians, or theta is equal to about approximately 1.66 degrees. That's a really good problem. Again, the important thing to this, and a lot of textbooks don't explain this very well, is to draw something like this when you have this situation, because you know if this gear is going to twist, or the shaft in here is going to twist this much, then this one must twist the same. But again, they have different radiuses, so you can just do a ratio between the radiuses. All right. Again, best of luck on future problems.